So we have been looking at reactions and how we sort of measure the rate of the reactions, as well as this idea of the transition step, where we actually have this activation energy we got to get over for the reaction to proceed to completion. Our last piece to kind of think about when we think about our collisions and our particles is what we call molecularity, actually thinking about what has to happen with the particles in order for the reaction to occur, because there's a misnomer. If you think about the reaction on the screen here, A plus B plus C going to D, as we have it written, it wouldn't work. It just wouldn't. This is like asking a juggler to throw 3 balls into the air at the same time and have all 3 collide simultaneously to form one final thing. 3 particle collision simultaneously doesn't happen. We have 2 collide and then the third one hits, or maybe the second and third one hit and then the last one hits, or maybe 2 hit and then they form another third, maybe 2 hit and 2 hit and then they all come together. Anyway, as it's written, this reaction wouldn't work. We can't have a three particle collision. And so we have this thing called mechanisms. The idea that our reaction is going to take place in a series of steps to get us to that final overall reaction that we've been kind of describing with our balanced chemical equation. And so we often break them down into mechanistic steps, or our elementary steps, the individual elementary parts that occur. And so there's a couple different ways you can write this. You could have one thing change into another thing. We would say that this is unimolecular, or one particle collision, or involving one particle. Unimolecular. If you're going to write a rate law for it, well, we would just say that the rate is dependent upon how quickly A changes. We'd say it's directly related to the concentration of A because it's unimolecular. Just depends on how much A you got. It's the only thing that could effectively change the rate of the reaction is how much of that substance you have. You could have 2 A's reacting to make a product. That would be bimolecular. Our rate here would be A's concentration squared. It is exponentially related to your molarity on A to the second order. If you had A and B reacting simultaneously to form a product, this would still be bimolecular. If you were to look at our rate law here, it would still be second order overall, but it would be first order with respect to each of your concentrations. So just thinking about how we're kind of just breaking it down into smaller steps, that actually makes sense. That we could, have one thing maybe break apart into something smaller, or have 2 things collide. Totally can have that. The thing you can't have is a termolecular step or elementary reaction, because you can't have a 3-body collision simultaneously. 2 are going to go and then 1. And so termolecular, not going to be a thing we're seeing, because it has to either be uni or bimolecular. Cool. So let's think about how this could start to fit together then. So for example, say this was your steps and you want to find the overall. You want to figure out what your overall reaction is given these mechanistic steps. Well, the good news is it's a lot like Hess's law, where we can actually add the reactants all together, add the products all together, and then get our final or overall rate law. And so that's what we do. We would say that we would add up our steps. We got NO2Cl and an NO2Cl. So it's 2 NO2Cls reacting with 1 Cl to form, looks like 2 nitrogen dioxides and 1 chlorine. And oh, wait a minute, we got a chlorine here and a chlorine here. If they're on opposite sides, they cancel. So that Cl is an intermediate, which makes sense given that it is not in, we know that chlorine wants to be diatomic. And so we would just add them all up. Molecularity is going to be the sum of the reactants for each step. So if we're thinking about our parts, we're going to add 1 and 2 together. Our chlorine, monochlorine here is an intermediate, made it and then used it up. And so we end up with 2 NO2Cls, excuse me, I misspoke, on the left-hand side. And then we have, looks like 2 NO2s and 1 chlorine molecule on the product side. If we want to think about our molecularity, we would say that step 1 was unimolecular, only had 1 reactant. And step 2 was bimolecular, 2 things colliding to make our overall substance. And then kind of the rate law for each step, we would just kind of write based upon the concentrations that we're seeing. So rate 1 would be some constant times concentration of our NO2Cl. Rate 2 would be just our concentrations of our 2 reactants there. So just kind of pulling out, just splitting apart and thinking about these steps. You'll see here in a little bit why this becomes important when we think about our rate determining step. We're going to say the step, we're going to talk about it here just briefly. Cool. So here's one. where we could start to kind of look and see, just describing our mechanisms. Don't worry about the slow and the fast part yet. We're going to kind of dig into that. But as written, this overall reaction, it wouldn't work like this. We can't have three things all collide to make two things. Doesn't work like that. So we could propose some steps. We could say, well, maybe the nitrogen dioxide reacts with one nitrogen dioxide, reacts with one fluorine to make this kind of weird intermediate species for the fluorine in the middle, but then one of our products. Great, we're halfway there. Well, then maybe another nitrogen dioxide reacts with that intermediate to give us another product of that nitrogen, or excuse me, NO2F. And so we can then check, does this kind of mechanism, do these steps actually match what we see happening in the reaction? If we add up, if we sum them all together, do we get the overall? I think so. Our fluorines are going to cancel out when we add them all together. So this is just, I added all of these together, put them all on the same side, put them all together. Our fluorines cancel out. I've got two NO2s and a fluorine making two NO2Fs on the right-hand side. So yeah, these mechanism steps would add up to the overall. Would your molecularity make sense? It's kind of the second protocol, or the second piece we would look for. Do our steps either contain uni or bimolecular collisions? And the first one is bimolecular, second one's bimolecular. So yeah, it does. We're not going to dig into that slow step, kind of the rate piece quite yet, but we're going to layer that in a little bit later. Cool. Another one for you. On there, don't worry about the rate law here for just a second. We're just saying, do our mechanisms as kind of suggested here add up to the overall? And are they either uni or bimolecular? And I think if we're kind of looking, I think they are. We've got nitrogen monoxide and oxygen making NO3. Our NO3 then is reacting with another nitrogen monoxide to make two NO2s. Well, if we're looking at our intermediates, looks like the nitrogen trioxide species is an intermediate. It would get canceled out. On the left-hand side, I've got two nitrogen monoxides left with an oxygen. That matches. And on my product side, I've got two nitrogen dioxide. It matches, is reasonable. Both of our steps, as suggested here, are bimolecular, which means that this is totally a reasonable mechanism for what could be happening for the rate of this reaction. Because we know it can't be intermolecular. We can't have it occur as we actually have it written. Cool. Hopefully this is giving you a feel for this idea of how we can kind of deal with multiple particles in a reaction. We're going to spend some time looking at this, make sure we're feeling okay, and then we're moving on to our next piece.